Okay, so now let's see if we can come up, and we're not going to double check this on the computer. I'll just let you know if we found it or not. Let's see if we can find the formula for at least 2 people have the same birthday. So what do we need to be thinking about in this situation?
So we need to do kind of the same thing where we fix 2 people. Like we just make 2 people have the same birthday, and then we just don't care what the other people have. Like they could have the same. They could also have that birthday. There could be another pair in there.
Yeah, so that's tricky because we're going to be over counting when we do that. We'll force 2 people to have the same birthday and then not care about the other people, but that's going to create situations that we could have counted already. In other words, we could pick A and B to be the people who have the same birthday, and then not care about the people over here, but C could have the same birthday as A and B. But that would be, the reason this is going to be over counting is we could later pick A and C to be the same people who have the birthday, and then B shows up. Okay, so we would have counted this situation more than once.
Yeah.
Okay, so we have to be really careful about the counting here. So we have to identify some problem, some feature of the at least 2 people have the same birthday that we can identify to make it easy to count.
Well, maybe we could just count 1 minus number of people who don't share any. Like the cases that have no birthdays in common.
We do complementary count.
Okay, why is that a potentially interesting approach?
Well, because we have a lot of cases to count, and all the cases kind of overlap over each other. So it'd be hard to separate it out into what we need to count.
Okay, so give me an example of the cases. If we're going to try to count case by case, what are some cases? If
we could count
like
1 pair
having the
of
same
2 pairs of 2, and then there could be 1 pair of 2 plus 3 pairs.
3
of
or
3,
more than that. So
yeah, so it's wild. There's all kinds of cases
that
here.
we miss.
But they all have something in common, all of these cases. What's the important thing they have in common?
So they'll have at least this. There's at least 2 people who share a birthday.
Okay. So why is complementary counting here useful?
Because it's a simple. This is a simple case, and there's not going to be any overlap between this and this.
Right, that's the thing that these all have in common, is they're not in this set. So the thing that's not these things turns out to be really easy to count. So we want to figure this out, what we want to do is 1 minus our n people all having what?
Different
birthdays.
And so how many choices do we have for the first one?
366, 368, 5, 364.
All the way down to what?
So it's
366 minus
n minus 1.
minus n minus 1. Right, that's because now we have n buckets.
Yeah.
And then divided by 366 to the end.
To the n. And this is the formula that's going to tell us n is approximately 23 to get 50%. Am I on screen here?
Yes.
Okay. So it's a surprising thing. You only need 23 people approximately. Does that surprise you? So, well, actually, sorry, before I jump to that, does the complementary counting make sense?
Yeah, we're just counting when everybody has a different birthday, and then you're subtracting that from the total probability.
Right, and that's sort of the critical thing here, is you want to count the opposite. But now let's go back. Does 23 surprise you?
Yeah, I mean, it's surprising that it's so low.
It's so low.
Right.
Like if you just said that you have 23 people in a room, and that 2 people in that room have the same birthday, someone who didn't know this could be surprised by that.
Yeah.
It's a big jump from 0% to 50%. So it's from having 2 people basically 0%. 23 people is 50%, but you have to go up to like 367 people for it to be 100%.
Yeah, it's kind of a big. You get the first half in 23 people.
But then basically the larger amounts of people don't really matter.
So I'm going to show you one kind of simplistic way of thinking about it, where it becomes a little less surprising. So I'm going to pretend we have 24 people, right?
Okay.
Okay, and I'm going to try to spread them out to avoid collisions. Okay.
So
Yeah.
put 2 in each
To
month.
each month.
So essentially what I do is I just try to spread them out in the different months. I mean, obviously this isn't exactly right,
Yep.
but then I have 24, so I'm going to go back and put 2 in each month. Okay. So now pretend each month has roughly 30 days, right? So there's a 1 in 30 chance of collisions, hand waving, right? And how many,
There's 12.
so how many, just right off the bat there, how many months do you think I would need to have a 50% chance?
So 15 months.
Right, and I have 12.
So you're close, a little less. But
So this is a way of thinking about it that makes it a little bit less surprising, right?
Yeah.
But right off the bat, 23 people and a 50% chance seems really surprising. Here, when you try to spread them out, you can see that you can have accidental collisions. And it's still a little surprising. It's not shocking when you think about it this way.
Yeah.
All right, good work this morning, guys.